What I want to do today is give you some ideas on how to perform LCA or lifecycle assessment calculations with visuals, and also talk a little bit about the underlying principles that you can use. So when you want to do these kinds of calculations, you basically have two options. You can either go with materials from the Revit file or your IFC file. We'll be talking about Revit today. Or you could work with the types that Revit gives you. So this one here can make sense when we are talking about later stages or very well maintained models where you're really sure that all the material layers are kept well in your model. What I think is better usually for early stage analysis is to go by types. And that would typically mean that you take, for example, your walls, you take the area of the wall, and then you multiply the area by a unit rate that is specific for the wall type. And that is what I want to show today. And this is where the concept of build-up tables comes in. And you can think about this as sort of a way to externally define your wall types, but also kind of your doors and maybe your railings. And this is so that you can have some experts or some curated set of LCA information that does not live in your Revit file, have that as the central piece of information and map that into your Revit files. And the basic concept here is quite simple. You pretty much have a table with only 3 columns. You have some sort of match key that you will use to connect this information from this table here to your Revit model. Then you have a base unit, which influences how you will calculate. So if you're going to take the area from your Revit file, for example, on walls, or if you're taking each piece of the model individual, which would, for example, mean a door, and you just attach a global warming potential number, or any number actually, to that door. Or if you're working with railings, it might make sense to just take the length of them. So, and these numbers here, so this information represents a single type in Revit. And of course, there is multiple materials that go into each type. And for example, here, this could be a wall where you have some structural concrete that has a global warming potential number. There is some rebar in this concrete, and that has a number. There's some insulation, and then there's cladding. And this information is per 1 square meter or per 1 unit of that element. So for example, if this was a door, then of course this would not be in square meters, but it would just be the overall materials used in that type of door. So there's 2 basic matching patterns that we could use. One would be by the Revit type name, and that would mean that you have a pretty fine grain matching between Revit elements and your build-ups here. This may or may not be what you want. If you want that level of control, that's cool. If not, I would probably go for some kind of bucketing where you group your, not literally group in Revit, but from a data perspective, you identify all the exterior walls with some parameter that you can define yourself. And then depending on what kind of breakdown you need, you identify all the exterior doors, maybe all the railings, and maybe for floors, you split them into structural floors and flooring. And each of them has a base unit, what you want to calculate with, and then the global warming potential. So this kind of means that you have one big spreadsheet that has all your LCA information by either a type or some other form of matching parameter. Now the question is, where do you get those? And I think these are the main options that you have. Either your company has this stuff already because you have a department that deals with this. You can search for these things online to have some generic mapping for exterior walls per square meter in the area where you're living and where you're building. You can make one manually if you are an expert and if you know what you're doing. Or you can make an AI agent produce one. This is, of course, has to be taken with a grain of salt. But for this example, this is what I did because I just wanted to test it out. And this is how I did it. If you want the exact markdown files and steps that I used, you can just contact me and I'll send them to you. But the general idea is that with using an AI agent, you could try to make some generic build-up list that you can carry on from project to project, or you could make this per project and really try to get quite accurate, because the method that I used was able to produce all the build-ups for all the elements in this model in about 30 to 60 minutes with some back and forth. And you want to do that with something like Claude Code or Codex, pretty much a very strong agentic desktop app where you can point it to two kinds of inputs. One is a material table that can be downloaded. So for example, in Germany, that would be the Ökobaudat. In Switzerland, it's the KBOB. I think the Nordic states, Denmark has LCA Big or something. So pretty much some source of information where you have materials and you have the global warming potentials for the phases that you want. And that's typically going to be A1 to A3. And then you want to supply the agent with all your BIM types. So that could be an export of all the wall types or all the door types. So pretty much all the types where you want to have a build-up for. And then the prompt goes something like this. You could say, use a sub-agent per type to create a build-up. Use all available information or data from the type table, as well as your world knowledge to make informed estimates. And what we're trying to do here is we want to have one central agent that commands multiple sub-agents so that the context window of the main agent is not overflowing. And since there's going to be a lot of thinking going on for each of those wall types, it's pretty good to use sub-agents for that. And again, Claude Code or Codex can spawn these, and they can even spawn these sub-agents 2 levels deep. So you could be running one orchestration agent and you feed it some high-level guidance. It's going to be one markdown file. And then that agent feeds or spawns 3 other agents, and each of them gets supplied by a more specific markdown file, one for all the area-based types, one for the linear types, like the railings, and one for the entity types, like doors and windows and furniture or mechanical equipment. And then each of those sub-agents on this level here, they will again spawn agents for each of those types here, and they will be kind of tasked with the second part of this prompt here. to just look at the information that they have. They see the type name, they see a description, they see a width, maybe they see a fire rating. The more information you can provide, the better. Of course, it has to be accurate information, but they will then kind of figure out what may go into this type. And of course, it is very helpful if you have some kind of build-up information in your type names or somewhere else. You could maybe also pull up some information from the wall construction here, but as I said, this is more an approach where you don't necessarily already have the wall construction defined. So, and then the idea is that these sub-agents here, they go through all the types, they create kind of one row of a final Excel file for you one at a time, and the information travels up, flows up through the agents, and then the orchestration agent returns you a table that looks like this. What you want in the end is a pretty simple table. Okay, so that's the background. Now, how does this look in practice? So, 3 steps here. First, we export all the data for the agents. Then we bring it back and do the calculation. And finally, we can do some analysis. And here, oopsie, this is just an example on the 3 main types of calculations. So for this, I've just taken all the railings. And as you can see, there's a bunch of empty stuff here. I included that just to show the agent that it's empty and it has to kind of guess a bit. But you can see, if you're familiar with German, that these type names are very descriptive, and that has helped the agent a lot to come up with some good estimates. Next one, this was the doors. Well, here you can see all the doors that are in this model by type here. And for these ones, I went in, because just the sizings of the doors don't really say much. I went in and added some type comments manually just to add some more information for the agent to work with. And then this was the example for the area-based elements. In this case, it's walls, but it could also be floors and roofs. For this one, the function is typically quite useful if it's exterior or interior, because yeah, that makes a big difference. Also, above ground and below ground would be a good information to provide here. Yeah, and then you export all those. It goes like this. You just export this to Excel. And then you switch over to your agent software, use the prompts as I described, and let it run. And at some point, you will be presented with an Excel file. So this down here is the Excel input that we can take. And that is this guy here that my agent has made for me. And I'll just open up a table preview for you. Import it, of course. Okay, so you can see that these are a bunch of type names, and these are door type names. These are wall types. And here's also the railings. And you can see that the basis unit has been kept alive throughout the agent flow. And then the global warming potential per unit. So this one is the GWP per piece, so per one door. This one here is the global warming potential per 1 square meter. And down here, this is global warming potential per 1 meter. And then what you do is you take your model input. You can grab it from here, model input, Excel input. And I'm letting this run on all the categories, so I'm just not picking any category. That's going to use all of them. And then I've added a bunch of parameters here, and we can talk about those a little bit later. But the main thing is that obviously you need to provide the type name, because that's what we use to join those 2 tables together here. So we take the Revit type name and then the type name from this Excel input. And then, of course, the area for the walls and the length for the railings. And this is where a system like this one is really handy because this system doesn't restrict you to only pick area when you're working with walls, but you can essentially try to get the area from any kind of element. So this makes it just much more streamlined and prevents that you have to work in different tables. Yeah, and then we're just using this add columns node here, which is this guy here, to define a new column. This is like a temporary column. If you've watched my previous video, I think I've mentioned it there. This is not a column that exists in Revit. It's just within this node graph. Oh yeah, and I should probably also show you the output of this one here real quick. So this is after the joining. And you can see that the type name here, this is the type name from Revit, and this one is the type name from Excel. They have been used to match. And this has pretty much just taken the Excel data and has added it to each row here. Okay, and next up is the formula that we use to do the actual calculation. And that's this formula node. We want to output the result of our formula into the GWP per element column, which is the one that we create here. And then we're using this case when function. And this is just a nicer way of writing a bunch of if statements. And if you've used formulas in Revit with the calculated fields, those if statements may be quite familiar to you, except that this here can work with strings in the formulas. So these tests, what they say is, the first condition is if the basis unit equals M2, then take the area from the Revit file and multiply it by the GWP per unit from the Excel file. Else, if the basis unit is meters, take the length and multiply that by the basis unit, by this GWP per unit. Else, if none of that is true, so if it's not M2 and not M, then we just take this GWP per unit, because that means that we're working on pieces, right? That is the last option, is pieces. And in that case, we don't need to do any calculation. We just need to make sure that this ends up as a number, because this is a number parameter here. And we just take that and add that to this element, because we're working element by element here. Even though we had created information per type, we've joined that to the Revit file on a per element basis. So this function runs once for every element in the Revit file. And then this is what it outputs, which is the number that we're interested in is this final one here. And you can kind of see that this was the basis unit of M. The value per unit was minus 69, and the length was 0.81. So minus 6.5 is fine. Negative GWP numbers come typically from wood. You can discuss if that's fair or not, but typically using wood reduces your carbon footprint in some calculation methods. All right, and then we can take this group and aggregate node and just quickly see what's going on. So in this case, we're grouping by the type name, and we're building the sum of the GWP per element, which is giving us the GWP per type. And down here, we're doing the same for the categories. So we can see what is the category with the biggest GWP. And then to do some, so this would be like a high-level overview here with your graphs and charts, but maybe you want to do some deeper analysis. And for that, it's good to write the changes or the calculated values back into Revit. And you do that. In this case, I just added a rounding function here because I didn't want to have all the decimal places there. So I just added another formula. Oh, and I chose LCA result. And that is a parameter that I've made in Revit before. So this can be a shared parameter or a project parameter. I kept it simple and made a shared parameter, project parameter, sorry. And this is the LCA result. And the only thing, and this is again typical Revit madness, for some reason, so we're dealing with numbers here. So obviously we want this to be a number parameter. The strange thing about Revit is that the area data type, which is a number, is the only number parameter type that can vary by group instance. Super strange. Why can we not just have the number parameter different for every item across groups? But hey, that's how it is. So that's why we have to use the area parameter type here. Doesn't make sense. It is how it is, and that's how we can store the number into Revit in a safe way without running into all those grouping issues. And then this parameter is just for all the categories here. So that's the parameter setup, and that's the one that we're writing into here. And you can see here that this is, if we go all the way here, what we've done is we've taken the GWP per element and put it in the LCA result. This is what it does. GWP per element, rounding it, putting it in there. So this also gives you an idea that you can just move parameter values between parameters with this method here. Okay, and then create changes. So that's the way how you get stuff into Revit. That's this node, create changes. You pick the parameter that you want to compare against the content of the current Revit file. And then you say create changes. It will add this little table for you here. And it has now compared the value that was in the graph to what was in the model. And in the model, it's all 0. And it has kind of staged these changes here for us. And then I'm just hitting approve all and send to Revit. And that is moving all the data into Revit. You don't really see anything in Revit, but it is working. And then clear those previews here. So now you can see that we have all those values here. And our final analysis can be done in the same canvas here. And this is just an example what you can do. So for example, if we start from the left here, there is this one, which is the per unit one. This is from an earlier run that I did. I didn't write that into the model just now, but it is information that I've previously written into the model with kind of a similar approach. And this allows you to color the model according to how much CO2 or how much GWP is there per element type without accounting for the size of an element. So just what is in one unit. And then this one here is giving us buckets of data. So we are again using the per unit measurement, and then we're just making buckets. So below 50, between 50 and 200, and above 200. And I think this is a pretty meaningful visualization where you can really see, okay, what are the bad boys, the main drivers of your emissions in this model. And what we can do is we can go down to the level of the individual element, and that is this one here, where we are taking the LCA result, which is the calculated result per element. And unsurprisingly, those giant walls here that span across 3 floors and are the longest walls in the model also have the highest impact. I think if this building was modeled level by level, this visualization would make more sense. But sometimes it's just modeled like this. Yeah. That is the overall idea of carbon analysis with visuals. I hope you learned something. I know this is a huge topic. It's a bit complex. But I really think that since this topic is inherently complex, tools that promise you to do like a one-click solution are oversimplifying. And I think this one here gives you a really good level of control. You have control over the individual steps, but it's still repeatable. It is pretty automated. And I think it's a good mix between accuracy, control, and ease of use.